When we use a z distribution, we have the population standard deviation. We know it. But what happens if you don't know the population standard deviation? Well, you use a t distribution, which is also a bell-shaped distribution like the z distribution, but it looks a little different, and we'll go over that in a little bit. But when you don't have the population mean and you're trying to estimate it, then you're probably not going to have the population standard deviation either. And that happens a lot of times when we're doing what we're going to do in this phase, which is confidence intervals and hypothesis testing. So this is really important for those two concepts in inferential statistics. And we'll go over those in the next videos. So use a t-distribution when we don't know the population standard deviation. Use a z-distribution when we know the population standard deviation. On the left, we have the standard error formula when we use a z-distribution, and on the right, we have the standard error formula when we use a t-distribution. And I'm going to use the sigma here for standard error when we use a z-distribution, and I'm going to use this s symbol when we do it for a t-distribution. And you see the only real difference in the formula is at the top. On the left-hand side, we have the population standard deviation, and on the right side, we just have the sample standard deviation. So the formulas are almost the same. We're just substituting the sample standard deviation instead of the population standard deviation. But the t-distribution is going to look different, and that's because of the distribution of sample standard deviations. So this is the distribution of sample standard deviation, and it is skewed to the right. So what happens is that the sample standard deviation tends to, or a good amount of the time, underestimate the actual population standard deviation. So that's why we have more to the left here. It's going to underestimate it a lot of the time. And even though we tried to correct this with the degrees of freedom, which is n-1, so we try to correct it by dividing by n-1, which are the degrees of freedom, when calculating the variance to get the standard deviation. And even though we do that, it still overestimates it, so it's skewed to the right. So at the top right here, we have the t formula, and it looks almost like the z formula besides the bottom, where we're going to use this new formula for the standard error, which uses the sample standard deviation instead of the population standard deviation. And remember from the last slide that the sample standard deviation will tend to underestimate the population standard deviation. So if that is smaller, then it's going to make the standard error smaller too. And then because the standard error is on the bottom of the t formula, it's going to actually tend to make the t bigger. And so now we're going to tend to have more t's here on the tails than we would if it was a z distribution. So that's why a t distribution is still bell-shaped and symmetric, but it tends to have fatter tails, unless you have really high degrees of freedom. The higher the degrees of freedom, the more the t-distribution looks like a z-distribution. And the degrees of freedom are n-1. So also, the higher the sample size, n, the more your t-distribution looks like a z-distribution. So the blue is a t-distribution with degrees of freedom of 13 and has the fattest tails out of these three. The purple is a t-distribution with degrees of freedom 5, and it has slightly smaller tails. And then the yellow is actually a z-distribution, and if we had really high degrees of freedom for a t-distribution, then that t-distribution would look really similar to the z-distribution. So the higher that your n is, the higher your degrees of freedom are, and the more the t-distribution looks like a z-distribution. To find percentiles for t-distributions, you can't really use a z-table or a t-table. There is a t-table, but it's more for confidence intervals. We'll learn that in just a little bit. But to find the actual exact probabilities, it's hard to do with a t-table because there's so many degrees of freedom, and so you would have to have 2 pages of probabilities for each degrees of freedom, and there could be an infinite amount of degrees of freedom. So instead, I'm going to have you use Excel, and it's not too hard. You just pick a random cell and say we have a t of 2 degrees of freedom of 35, which are in -1, so the sample size was 36, and we subtracted 1 to get 35, and say I want you to find the percentile for that. So you just put equals, and then in a random cell, t dot dis. So this one, this one gives you the left tail, so the percentile, and then just enter 2, comma, 35, that's your degrees of freedom, and always put true to get the percentile instead of just the individual probability. We don't really care about that here. So always put true. And voila, we get a percentile of 0.973346 for a t statistic of 2 with 35 degrees of freedom.